Okay, so last class we introduced the vorticity, that's the omega showing here, and we tell you 2 times omega is equal to the spatial differential operator across the velocity field. Okay, so as you can see, the definition for the omega with the different rotated axes x, y, z, and related to the different velocity gradients. As you can see, if we focus on the rotation axis is along the z, and we actually know it's equal to 2/1 dv dx minus the du dy. Okay, so if we go back to see the certain definition for the vorticities is equal to the differential operator cross with the velocity field factor. Okay, so I emphasize some ideas. If the vorticity equals 0, that indicates the fluid particle do not rotate. And the second, sometimes the region is always far away from the wall. Because if the fluid particle much closer to the wall, there is some viscosity effect along the boundary. So as I mentioned, the vorticity is very important associated with the viscosity effect. So if your fluid particle much closer to the boundary, that indicates the viscosity effect would be very important. So if your fluid far away from the boundary, that indicates there is no viscosity effect. Okay, so the 2 important ideas, if you actually know the vorticity is equal to 0, and you can conclude that the fluid particle do not rotate. And the second, sometimes you focus on the regions always from the wall. Okay, so we have the exercise. How can we apply the vorticity calculations to comment the fluid particle, the fluid is rotational or not? Okay, so as I mentioned previous slide, we know that we can calculate the operational differentials cross with the velocity field factor, right? So we can expand the cross product. So we have the I, J, K indicate the different directions along the x, y, z unit factors. And the differential operator, we have the dx and dy, and we have the dz. And we actually know the velocity field, we can represent it by u, v, w. Okay, the velocity along the x, y, and z directions. So if you expand the cross product, so we keep the I directions, and then we have the dw dy minus the dv dz. Okay, and the second we have the j components, so plus. And if we focus on the j component, it will equal to the u dz minus the dw dx, and the plus the final direction is along the k z axis, and we have the dv dx minus the du dy. Okay, so based on the cross product, and then we know what the u. Here, the 1, we have the u is equal to the 10 times x. And the 2, we have the v is the minus 10 y. Okay? And then here, this is the 2-dimensional velocity field. So we don't have the w, the velocity along the z axis is equal to 0. So based on the 3 velocity field, you can go back to see your equations. We don't have the w, so it's equal to 0, right? And the v the v velocity only as function of the y. So didn't change with the z directions. So we don't have these items. And then we check the z directions, the u differential with the z. But the z u is function of the x. So there is no z operators parameter. So we don't have this component. And we don't have the w velocity. So the final one is the k components. You see the v also didn't change with the z x, and the u didn't change with the y. Okay, so if you make the double check by yourself, and then you can see all of the velocity gradient are equal zeros. So we can comment that the final answers is equal to 0. And as I mentioned in the previous slide, if this is the vorticity, and the vorticity equal to 0, that indicates the fluid particle do not rotate. And then we can comment that the flow is irrotational flow. Okay, so the idea is quite simple. You just double check the cross product, and then you can see it's equal 0 or not. And then you can conclude that the fluid is irrotational or not. Okay, so idea is quite simple. So the next exercise is also related to the rotation of the fluid particle. So as you can see, the flow in here, that is similar to the Coulter flow. So you can see that it is a Coulter flow. Okay, and then you can see as well, I mentioned the Coulter flow. So we have the fixed boundary. The bottom is the fixed, and the upper is the free. So we fix the point in here. There is no any velocity, and the velocity will be changed along the will change it along the y-axis. So the different y direction, we have a different velocity magnitude, and at the top, the velocity is the maximum velocity. It's equal to the 2 centimeters per second. Okay, so for this question, what's the problems? As the problem is, please find out the amount of the rotation. The amount of the rotation. So that we need to require the answers for the delta theta. So that indicates how the fluid particle rotate angle, how large it is. Okay, so that's the problem, but we focus on the location at the 0.5 centimeter. So that means we focus on the point in here, the middle part of the fluid. So in here, the location length along the y is the 0.5 centimeters in here. And we already know the travel distance is 1 centimeter. The travel distance is 1 centimeter. So how can we answer the amount of the rotational angle for this fluid particle? So first, we need to know how the velocity, flow velocity at this point. If we know the velocity, and then we can calculate some travel times, because we already know the travel distance, but we didn't know what are the travel times. If we know the travel times and we have the theta rate, so that the idea is, if we have the theta rate, okay, that means indicate the angle change with the time. As we know, the theta rate is equal to, because this is a two-dimensional problem, and the upper is the y, and the right is x. That means our rotational axis is along the z directions. So we know the theta is along the z directions. It's equal to the 2 over, as I mentioned before, it's a dv dx, right? And the minus the du dy. Okay, and this is the theta rate. And how about the theta angle? The delta theta angle is indicate will equal to the theta rate multiplied the delta t, right? But in that case, we didn't know the theta rate right now. And we also didn't know how large the delta t in here. If we can know the delta t and we know the theta rate, and we can answer the questions, right? So the problem is, we try to our first purpose is we would like to understand how large the delta t we have. So we need to know the velocity at this point. How large velocity at this point. So first we calculated the velocity gradient. We calculated the velocity gradient. We know that the bottom to the upper is the 1 centimeters. And from the bottom, the velocity to the upper, the changes. So we have the v delta v velocity multiply the delta y. And we know that the delta v is 2 centimeter per second minus 0, right? From the bottom to the upper. And we know that the delta y is the 1 centimeter. Okay, so we know that the velocity gradient is equal to the 2, and the dimensional is the second over 1. Okay, this is the velocity gradient along the y-axis. Okay, so so we know that the velocity y, because we know the velocity will change when the y increase. And we have the velocity gradient is 2. So that indicates the velocity is equal to the 2 times of the y, right? 2 is our gradient, and the y is our functions. And this is a linear velocity. Okay, but right now the unit is equal to the centimeter per second. And we change it to the meter per second. So 0.02 y, and there is a meter per second dimensional. So right now we would like to calculate when the y is equal to the 0.5 centimeters. Okay, so and then you can put the number inside, but we can change the dimensional is 0.005 meter, right? So we can estimate the velocity y. This is the velocity. Right now the y is equal to the 0.005 meters. Okay, and then we put the number inside, so you can calculate the velocity and multiply 0.005. Okay, so you can know how large velocity at the location y is equal to 0.5. So it is equal to 0.0001 meter per second. Okay. So and then we know that the travel distance is the 1 center. Okay, this is our distance. So we know that how can we calculate the delta t? Because the travel distance is 1 centimeter. So the distance, if you use the distance divided the velocity when y is equal to 0.0 centimeters, and then you know that the delta t we have, right? You know that how much delta t we have. Okay, so you just put the answer all of the parameter inside here. So the 1 centimeter is equal to 0.01 meters, and the velocity is equal to 0.0001 meter per second. Okay, So you can calculate the delta T. Okay. So the 0.0. Maybe we keep we should keep all of the unit to the center meter will be much convenient, right? So maybe I rewrite here, and we have the y, because the 0 point is too much. So maybe I recalculate the y in here. So we know that the y is equal to 0.5 centimeter. So the velocity is equal to the 1 centimeter per second. That's much easy to calculate. And we have the 1 center distance travel. So we know that the delta T is the 1 centimeter travel distance divided 1 centimeter per second. So delta T is the 1 second, right? And then how large the theta rate? So we know that the theta rate, the function definition in formula in here. So we know that the 2 over 1 and the dv dx and du dy. And in that case, we don't have the v velocity, right? So we don't have the items for here. And so we only have the minus du dy, okay? Du dy. So, and then you can see the u function is in here. This is our velocity function, okay? So the theta rate will equal to and then you differential with the y. So it's a 2 over 1, and there is the minus 2. So this is equal to the minus 1. And because this is a theta rate, so the dimensional is the radius per second. The radius per second. So we have the theta rate, and we have the delta t. So we can calculate the delta theta is equal to the theta rate and multiply the delta t. So the minus 1 radius per second multiply the 1 second. So it's equal to the minus 1 radius. Okay? And the minus 1 radius, that indicates it is, if you by your right hand, so it's a minus. So you know that the cross is the clockwise cross, right? It's a clockwise rotations, because the sign in here is the minus. And how the degree? Because we know that the pi radius is equal to the 180 degree. So we know that there is the minus multiply the pi. Pi is equal to the 3.14 around, and we're over the 180 degree. So you can calculate the degree will equal to the minus, around the minus 57.3 degree. Okay, so you know that the 1 second pass, and the fluid particle will rotate it counterclockwise with the 57 degree. Okay, so as the time passes, the rotation angle will rotate much more rotation angles. Okay, but in that case, we only have the 1 second travel times. So only the 57 degree rotated, and the direction is clockwise rotate, because this is the minus 1. Okay, so this is application for if we know that the rotational definitions. So as we know that the Coulter flow is the rotational flow, right? And in the Coulter flow, we discussed with the viscosity, right? So that means some rotational flow will influence by the viscosity effect. But if your flow is a rotational flow, so that means the viscosity effect is not important. Okay, so that's the ideas. Well, we just try to practice based on the rotational equations. So right now we move to the next topic. We are looking for the Bernoulli equation, but for the irrotational flow. As we previous slide, the class we teach you the Bernoulli equation, but all of the Bernoulli equation we assume you pick up the one string line, and the 2 points at the string line are satisfy the Bernoulli equations. But how about if we change the flow conditions? We tell you the flow condition is irrotational. So how about the Bernoulli equation? Okay, so as I sentence write down in here, I tell you if the flow is irrotational flow, and then the Bernoulli equation can be applied between any two points in this flow. OK， 那这个很重要。我们之前就说伯努利方程只能用在同一条流线上的任意两点。可是如果我告诉你它是一个非旋流的时候，在流场里面任何两点都会满足伯努利定律，这样子我们就不需要在同一条流线上。OK， so we need to prove how we can apply the Bernoulli equations at your flow any 2 points. Okay, that indicates the flow is the irrotational flow, and then you can satisfy all of the 2 points for the Bernoulli equations. So the question right now is different. As we know that the flow velocity direction is going right. Okay, and this is the directions for the R directions. And so in that case, we use our right hand. So we know that the rotational is clockwise. Okay, the rotational is clockwise. So in that case, if we know that the omega in here is our angular speed. Okay, it's our angular speed. So in that case, the omega, because the clockwise, so omega is the minus omega, right? It is a minus omega because it's a clockwise rotate. So the omega is the minus omega. And then we go back to see the equation showing here. We call that the Euler's equation, right? But the Euler's equation right now we change the velocity accelerations is a acceleration along the normal directions. So we have a normal directions along the r-axis. We have a normal directions along the r-axis. And we in this chapter, I already tell you the an, the acceleration along the normal component is equal to the minus velocity squared divided r, right? And then I may decompose I take the velocity outside, the v, and the inside I still have the minus v d divided r. So I would like to prove the Bernoulli equations under these flow conditions. Okay, so the first one, I differential. The one important thing is dv and the dr. dv dr. And then let's indicate the velocity changes along the y directions. And this is our condition 1. And we have another condition. We know that the velocity will equal to the radius multiply omega, right? But right now in our case, the omega is the minus omega. Okay, it's the minus omega. Omega is the rotational angular speed. So in that case, if we go back to see here, let's indicate we need to calculate the dv dr. But the inside is the minus r W, right? I tell it's omega minus R omega. Okay, so I can calculate differential will equal to along the R is minus omega and minus R d omega dr, right? The d omega dr. And because our condition right now is rotational flow, and then we can assume the omega angle in here didn't change with the R. That indicates start from here and the R increase along the normal directions, but the omega rotational angle speed didn't change. Okay, if our condition satisfy these assumptions, so we can tell you this item will equal 0. If our flow is rotational flow, and then we can assume the omega angular speed along the y-r directions didn't change when the r increase. Okay, so the item in here, we assume the omega dr is equal 0. So we can finally, based on these functions, we only have a minus omega, right? And since we know that the minus omega also equal to the v divided the r, right? The v divided the r. Okay, so we can based on these ideas, and we have the minus in here. So if you do the comparisons along our first conditions in here, so we can replace the minus v divided r by the dv dr, right? Because the left hand side in here and the right hand side in here. Okay, and the continuous we also we put the new reorganize the equation. The an will equal to the v and multiply the dv dr. Okay, and then we know that we can do the integration, so we know that there will have the dv dr 2 times over 2 over v squared. 2 over v squared. Because we take the integrations, we integrate the v with the r, so we can put the v go inside, and then can replace the dv dr to be the 2 over v squared. Okay, so if we can derive this is our final acceleration along the normal component. So we put the equation into the Euler's equations. So we go back to see the equation showing here. So we can summarize the minus dn, the piezometric pressure P plus the gamma z, it will equal to the density, and the an right now is the dr and the 2 over v squared, right? And as I mentioned before, the Bernoulli equations satisfy, and the Euler's equation satisfy our flow is incompressible flow. Incompressible flow is indicates the density didn't change at any point. So we can put the density inside. So you have the 2 over rho v squared, right? Because the density didn't change when the r changes. And then because the differential, the right hand side is differential with the r, but the left hand side is differential with the normal components. So we need to change in here. So I use the dn, and the inside are the same. So 2 over rho v squared. But we still have the dn dr, right? The right hand side in here is equal to the left hand side. And we know that because the N and the R are the same directions, the normal directions is equal to the R direction, right? So the differential in here, these items will equal to 1. This item will equal to 1. So we can rewrite the equation is the N and the P plus the gamma Z will equal to the N and the 2 over rho V squared. Okay, and we can also rearrange the equation. So finally, we know that the D and the Dn and the P plus gamma Z plus 2 over rho V squared is equal to 0. And we can conclude that the P plus the gamma Z plus the 2 over rho V squared is equal to the constants. So based on assumptions for the irrotational flow, we also know that along the normal directions also satisfy the Bernoulli equations. If you use straight line, your direction is perpendicular to the straight line will be the normal directions. Along the normal directions, any 2 points also satisfy the Bernoulli equations. That indicates along the straight line 2 points at any 2 points, and along the normal component at any 2 points are all satisfy the Bernoulli equations. But only only under the irrotational flow, and then you satisfy these conclusions. OK， 所以只要这个 slide 主要就是在推导说，那如果我可以证明我的流况是非旋流，那我同时间就可以告诉你，在这个流场里面任意2点都满足伯努利定律。跟我们之前不一样，我们之前只推导说沿着流线的任意2点满足伯努利，那个时候我们不知道流场是不是非旋流。那如果我现在知道流场是非旋流，我就可以跟你讲任意2点都满足伯努利定律这样子。OK， 所以那时候因为我们不知道怎么去定义流体有没有旋转，那我们现在知道怎么定义了，那我们就可以再把伯努利定律延伸到非旋流的时候，任意2点都满足伯努利定律。OK， so that's the idea I would like to tell you. And then another conditions is as you can see, this is we call that the rotating flow. So what is the rotating flow? So we have a rotated axis along the vertical. Okay, and then we have the omega rotated angle. So in that case, it's different compared to previous slide because you by your right hand, the omega right now is the directions is counterclockwise. So in here, the omega is the positive. So we have the positive omega angular speed. Okay, so what's the problem for these questions? This is when the steady state, the condition. So you see the water is the horizontal line, but after we rotate, the water surface will become the curvature line. So and we know that the omega difference, we will have a different curvatures under for the surface waters. So right now we still start from the Euler's equations. So here is our Euler's equations, and you see we change the acceleration to the r directions. So the difference, what are the r directions? The r directions right now in here is the r is these directions. Okay, r is these directions because this is our diameter of the pipe along these directions. Okay, so how can we derive the Bernoulli equation for a rotating flow? So the key knowledge in here also, if we know that the AR, and then we can put the AR into the Euler's equation and try to see what's the final Bernoulli equation for the rotational flow. Okay, so the AR, okay, again, we know that it is the minus V squared divided R. And in here, our omega is the positive, so the V is directly equal to the R omega, right? Because the omega right now is the positive rotated. In our case, it's a positive rotated. So we can put the V squared. So there is the minus the R squared omega squared and the dr, right? It's dr. So we know that the AR is equal to the minus R omega squared. Okay, but you see the left hand side, what do we have? The left hand side we have the dr, but right now the AR there is no differential along the R directions, so we need to have the dr. So again, we know that there will be the maybe minus, and we keep the minus. And here we know that the maybe dr squared, and there's a dr also, but the inside is 2 over r squared, right? Because we do the integration for the r parameters in here. So, and then we still have the additional omega squared. Okay, so this is we need to have the d and dr operator in the acceleration. So we put this relationship into the Euler's equations. So we can rewrite the Euler equation is minus d dr, and there is the P plus the gamma z. There's our piezometric pressures. Differential with the R is equal to the low, but the AR is the minus dr and the 2 over r squared w omega squared. Okay, and then again we know that the density, because we either in incompressible flow, right? We already know our fluid is incompressible flow, so we can put the density inside the differential. So this is minus d dr, and the inside is 2 over low r squared and the w squared. Okay, and then you can reorganize the equations. So you can see the final, we know that d dr is equal to the inside component is a P gamma z, but the minus 2 over low r squared w squared will equal to 0. So the final one, so that's very important here, the difference compared previous slide. We have the minus in here. We have the minus in here. So we know that the final P plus the gamma d minus the 2 over low r squared omega squared will equal to the constant. So this is the equation similar to the Bernoulli, but the spatial formula for the rotating flow. And the significant difference in here compared to the Bernoulli equation on the previous slide, there is the minus. So you can make the comparison with the previous. The previous slide always the positive for the velocity items, but in here we have the minus. We have the minus for the low r squared gamma squared, and divided 2, the difference. Okay, so you need to keep in mind the minus difference compared to the previous slide. So this is the minus operator in here. Okay, so that's the idea very useful, because if we focus on our exercise, So this exercise is the calculating the surface profile of the rotational liquid. Okay, surface profile of the rotational liquid. That indicates we need to answer the curvature line in here. The curvature line in here. If you already know your omega is equal to the 4 radius per second. The 4 radius per second. And how can you predict the surface profile of the water line in here? Okay, so and you can see the radius directions is along these directions. Okay, so we pick up the 2 points. We pick up the 2 points in 1 and the 2. So you can calculate the first one. You can calculate the elevation difference. So you see the questions find the elevation difference between the liquid at the center is 0.1. So this is 0.1. And the wall during rotate, so this is 0.2. So we need to answer the Z2 minus Z1, how large it is. Okay, so this is our key questions we need to answer. Okay, so as you can see, the questions in here already know the condition is a rotating flow. So we can apply the Bernoulli equation for the rotating flow. So we actually know the rotating flow of the Bernoulli is the P1 plus the gamma Z1, right? And the most important thing is the minus in here is 2 over rho R1 square. And we have the same W, right? We have the same omega. Will equal to the P2 plus the gamma Z2 and the minus the 2 over rho R2 square and the omega. Okay, so how many conditions we already have is we know that the first condition, the gauge pressures for the P1 and the P2 are equal 0 because the 0.1 and the 0.2 are exposed on the atmosphere. So there is no gauge pressures. And the second, we know that the R1 will equal 0, right? Because the R1 is cross over the rotating axis. So there is no distance along the R1. Okay? So we only have the R2. And the R2, we know that the total diameter of the pipe is 0.5. So we know that the R2 is equal to 0.25 meter. Okay, so we can go back to see our equations. So we don't have the P1 and the P2. And our key questions is Z2 minus Z1. So we can reorganize the equations. So the gamma Z2 minus the Z1 will equal to, we don't have the R1, so this item also equal to 0. So it's equal to the 2, sorry, I changed the color pen, black. So 2 over rho R2 square. Sorry, I forgot to use the omega square and omega square. Okay, and reorganize the equation. So we know that D2 minus D1 and the right hand side is equal to 2G omega square and R2 square. Okay, so you can put the number inside in your equations. So we know that the omega is the 4 radius per second, and there's a omega square, so the unit is the square. And divided the 2 times gravity is 9.81 meter per second, and the R2 is 0.25 meter square. Okay, and you can use your calculator to calculate the final answers. So I use my calculator to check the number is correct or not. Okay, so it's almost around the 0.051 meters. Okay, and you base on the equations, general equation showing here, you know that the r square and the left hand side is d2 minus d1. The function looks like the parabolic. The function looks like the parabolic, and the defined z elevation difference is equal to the r square. So that's why the water surface looks like the parabolic. Okay, so this is and in that condition we call that is the forces fault test. forces fault test， 我们说这个叫做强制涡流的实验。你让它是旋转，这个是你强制加压给它的。正常来讲，它是不会旋转的嘛。那你加压了一个旋转的 omega， 所以你就会看到它有一个涡流的现象，因为它是一个 rotational。OK， 那等一下我们下一堂课再来讲。我们这边就先让大家休息一下。